Okay, launching the YouTube broadcast. Okay,
Looks
launching
like we're
the
in
YouTube broadcast. Inception mode. Okay,
It is April 21st.
Inception mode.
This is
CS-030.
April 21st.
We're working on chapter 17.
This is CS-030.
April 21st.
Shifting out of Inception mode.
Shifting out of Inception.
All right. Let's try this again.
All right, let's start working through our checklist as we arrive. There we go. I'm looking at my checklist over on a separate window here, and I'll read it off. It should be the same one that we've got in the classroom. So make sure you're activated on VPN so that you can get your voice in game if necessary. Find a quiet location. Tell your roommate that you are in class and you're not playing Fortnite, despite what it might look like. Put on your headphones so we don't get echo when you speak. Shut down any extra apps or browser tabs that you might have open. And I'm going to do that for a sec, make sure I'm good. Okay, I'm all set. Open Canvas so you can see where we are schedule-wise. And you may want to open Eclipse, although I don't think I'm going to be doing Saros today. Open up Firestorm and rebake your avatar. Avatar health, rebake. And then set up your environment. That's enough music, thank you. Make sure that under world and environment, you are set to midday, good. Let's make it to our classroom. I'm trying to get there myself. Make sure you've got your name tags on and then check in at the attendance machine. Looks like we've got everyone here. Great. I'm going to ask Dodger to settle down a little bit. You need to lay down, buddy. Dodger's looking a little under-resed this morning. Oh, no, there he goes. All right, he's good to go. All right, so today we are starting on chapter 17. Which is trees. Trees are super cool. We are ending our discussion of searching and sorting, which is what we were looking at last week. And as our final programming assignment is going to be a drone world assignment, let me go ahead and walk us through what the last one is going to look like. And let me just open us in prayer for a sec, as we've had sort of a big couple days with things going on campus and around the world. All right, so if you will pray with me for a second. What does it look like to pray in a virtual world? Here we are. Okay, double broadcasting, thank you. All right, dear Heavenly Father, wow, so much going on all around us all the time. So many channels to be aware of what's happening through news media and social media, normal old school media, talking to people through different channels and medium. I know that settling in to do this work is the long horizon work, Father, training up our skills and understanding so that we can make a difference in the long term, although we are constantly assaulted by things in the short term that need our attention, that are monumental and important, Father. We pray especially for the kinds of things that were going on over the last few days with the George Floyd verdict, Father. We pray for justice, Father. Just broadly speaking. And we know that that does not come easy or cheap or fast. And so at the same time as we are working to see that and all the different ways and facets in which it needs to be brought to bear in our country and our community, we also want to invest in our skills for the long term so that 20 years from now we can still be making a difference. So we pray these things and a blessing on our time today. Amen. Okay. Great. All right, so we are starting chapter 17, so we need a Dodge report. We also need to talk about our drone challenge. Why don't we talk about our drone challenge first, and then we can move into our work on our chapter 17. All right, so our final drone challenge has been posted. Let me break off a tab and show it to y'all. There it is. And let's get that on screen. All right. So the drone challenge number 3 is the final challenge, and it will be building on the previous ones. What you are going to do is there's not a different backstory, same scenario, except that the world has gotten a little bit more complex. You again are going to turn in a new third version of your mycontroller.java file. And if there are any separate classes that you need to support that, you can turn those in as well. Those separate classes should not be modified versions of my classes, but if you need some kind of helper class in order to make your class work, you're welcome to turn those in as well. You can also implement them as inner classes within your Mind Drone controller class if you'd like. Don't submit your entire project archive, just the Java source files that implement your controller. And I only want one submission if you are submitting it as a group, but the comments in the code should reflect who it belongs to. Groups can be up to 2 people. All right, so what this challenge is it's making it a little bit bigger. This time, instead of 5 drones, you're going to have 10 drones. Each company will have 10 drones. And the same drone controller will be controlling all 10 of them. There will be one instance of your drone controller controlling all of your drones. So your instance variables will be shared across all of the different event handlers. One thing that's different about this run is that you are going to be competing against all the other students or groups in the class. And so we're going to put all of your drone controllers into one world, and we're going to simultaneously run them along with all of the drones controllers that I've written. So there should be, I don't know, 15 or so different companies running at once. In order to increase the demand and make that something that is comparable, we're going to have 100 different locations. So same map, but there's going to be 100 different locations, and a handful of those new locations are going to be automatically generated or randomly generated. There will be 1,000 passengers that are populating those locations. And 2 important changes for your controller this time around is that drones will explode if they run out of charge. And so what that means is that to avoid exploding, you have to make sure that before you send your drone to a destination, that it's going to be able to reach that destination without blowing up. The other change is that your drones can carry more than 1 passenger. They will carry some number of passengers, up to 10, but each of your 10 drones will carry a different number of passengers. And so that varies based on drone. And that's something that your drones can ask themselves through a method call if they're interested in changing their behavior based on that. All right, like the previous 2 instances, this code can be obtained by checking it out from GitHub. I recommend doing that fresh, the same way we did for Drone World 2. So saving the code that you've currently got in a location that's not in your Eclipse directory, perhaps by copying it or moving it from your file system, and then starting a new project following the instructions in Drone World 2, but this time the branch that you're trying to check out is called Drone World 3 for students. And I just committed that this morning. So if you got a copy or something before this morning, you'll need to do it again or pull the updates if you know how to pull the updates. In order to be able to tell how far 2 locations are, you can use the distance calculator function, which is built into the simulator. There is already a class that will tell you how far apart 2 locations are. So distance calculator.distance, and then the 2 latitude and longitude you care about. And then if you want to know whether or not your drone is going to blow up, this is the basic formula that you can use for that. If the distance that you are going times the drone discharge rate is greater than or equal to 1, then your drone is likely going to blow up before it gets there. So if this expression is true, then a drone with full charge will blow up before reaching the traveling distance. If you would like to build in a little bit of margin to that, you could lower the 1.0 number and say, hey, I want a little bit of safety margin in that, so I'm gonna act as if I will blow up if that number is ever greater than or equal to 0.9, for example. So in conjunction with the new third version, there's also a new rubric, and so here are the different levels. So starting at the bottom, if you turn in a mic controller class that compiles, you will get a 50. If you are able to deliver 1 passenger, you'll get a 60. If you can deliver 2, you'll get a 70, and 4, an 80. If you deliver 10, you'll get an 85. 20, you'll get a 90. 40, you'll get a 95, and then you can get a 97 if you beat 4 of the reference controllers. So those are the controllers that I offer. You can get a 100 if you beat all of your peers. So you're the number one controller, number one Uber drone controller for the simulator. And you can get 105 if you can beat the Borg. The Borg is a 5th reference controller that I've introduced that is my best effort at writing a drone controller. I think the thing that in particular that the Borg does is that it coordinates behavior among the different drones. So each drone doesn't act independently. It looks and pays attention to what all of the drones are doing and tries to optimize behavior in that way. All right, so let me see if there are any questions. And while I'm checking to see if there are any questions, let me pull up the simulator and show you what it's going to look like when you run it. Everything else is pretty much the same in terms of the simulation controller, etc. You obviously don't have access to the other people's code, so you can't run you can't run a practice run against other people's code unless you do a little bit of work and incorporate them into your particular. If you work with another team for some reason and give each other your code, which is probably a little risky, but in any event, here's what it would look like if you run it. Oh, I'm not running it in fast mode, so this is going to take a second. So if you have questions, feel free to pipe up and ask them. We'll just wait patiently. Oh, so patiently. Yeah, I could do the Dodger report while we wait, I suppose. All right, let's give that a shot. All right, so while we wait, here's our Dodger report. I struggled to get some photos that worked well, but here's the Sunday. This is probably our last Sunday doing church at home because our family's been almost fully vaccinated, everyone that is eligible. So our Sunday routine, which involves making bread and just having church at home, is coming to an end. And so this is Dodger. Dodger is always trying to get the crumbs from under his master's table, if you know what I mean. Does not get any of the bread, unfortunately. This is him yesterday hanging out with me while I was grading on our back patio. He was moping about. I'm not sure what his issue was yesterday, but he was in a bad mood. These are other photos I took. We'll ignore that. Oh, back to our world for a sec. Okay, so here we go. Here's all of our competitors running. It's the frame rate's kind of slow because I got so much stuff running on my computer at one time. But what you can see is that the world has, let me see if I can zoom out a little bit. The world has gotten a little bigger. There's a lot more locations. You see that there are explosions that are going up as some of the drones, which are not aware of the fact or that are not operating under the understanding that they will blow up, are blowing up and crashing, leaving carcasses of spaceships and smoke. And let's see if we can zoom around to get a better view. There we go. All right. Some remain operating. You can see that there are 1, 2, 3, 4, 5, 6 out of the gate. There's a lot more ninjas in waiting. You can see that the Borg is at the bottom doing its best to deliver passengers as fast as it can. I just want to let it run for a second so that you can see, you can kind of see it if you're looking carefully, but down in the bottom left, you can see that the fourth one down, the Promiscuous Drone Company, that has a chunk of its bar which is black. And that chunk of the bar which is black means that some of the passengers that were being carried by the drone have died because the drone has crashed because it ran out of charge. And so that black indicates that some of the drones have gone down. Greedy and Associates has a very, very small little chunk black there. I'm not sure if it's coming through. The Borg has about half of its capacity is red, meaning it's carrying a bunch of ninjas. About half of the bar is green, meaning it's delivered those ninjas. And so far, it's doing okay with not blowing up on distance. It looks like maybe first 4 companies, the drones have all blown up and are just sitting on the ground, not doing anything. Promiscuous drone having loaded some passengers before it blew up. All right. All right, so I won't make that run till the end, but that's kind of what you should see when you get it out of the box if all is going well. And I usually set it up as a bracket, a tournament bracket to see how folks are doing. We'll see what makes sense. Well, why would I do a bracket if I put everyone in it? I'm not sure. I'll double check that. Maybe just run multiple runs. So anyway, here is last Dodger run. Let's see. This is a burst, and I could not for the life of me get anything to work this morning. So here we go. See if we can see Dodger. This is dinner time last night. Dodger knows one particular word called dish, and when he hears dish, he gets very excited, and he is able to make quite a tall leap. And he tries to lick my face when I say dish, because he wants dinner. So he gets up there pretty high. Good for him. All right, and I think that's all I got for Dodger today. This was him this morning. No, this was him last night, trying desperately to get me to feed him dinner, but he had already eaten, so bad dog. All right, let's shift gears. Let's talk about tree structures. Tree structures are really cool. I think they're pretty neat. And there's a particular way in which we think about them in computer science. There's very little in computer science that I don't think is cool, so there's that. But here we go. So what we want to do in this chapter is to give you an introduction to the language and terminology of trees, and then also to give you a particular implementation of trees. This is following on a sequence of data structure developments that we've been looking at, starting with just primitive data types like the int and the double, looking at the object-oriented versions of them, capital I integer and capital D double, and then the other associated ones as well. And then we moved into talking about the Java collections framework, our first foray into thinking about the way in which we can use data structures to implement different kinds of patterns of data that we have in our world, things like lists and maps, and then special versions of them like linked lists and array lists, tree sets, hash maps, tree maps, all part of a hierarchy of definitions and interfaces of data structures that we are interested in. Well, the tree is another one, and a tree is used in order to implement some of those data structures. So, for example, not surprisingly, when you implement a set as a tree set, it's using a tree in order to implement the behavior of a set. And when you use a tree map, it's using the implementation of a tree in order to implement the map behavior. So in some ways, depending on what's happening, a user of these classes don't necessarily need to know that a tree is being used. But if you want to implement them, you need to know how a tree is being used or how you could use a tree. Furthermore, the tree is just generally a kind of data structure that's very helpful in a variety of different contexts. It's used in all kinds of different ways in computer science. It goes kind of in lockstep with recursive algorithms. Trees are very naturally recursive, and so computer science trees are very naturally recursive, and so we need those recursive algorithms in order to do some of the work with trees. So our goals are to study trees and binary trees in particular, understand how binary search trees can implement sets. Hopefully we will be able to talk about red-black trees and how they help us to get high performance set operations. Think about methods of tree traversal. I think that's very important to know. And then also look at how it can be used for heaps and priority queues. So it's a very data structure heavy lecture. So for starters, why is there this picture of a tree that's upside down on this slide? Well, that's because although we use the word tree in order to describe this data structure, the way in which we visualize it is typically more like an upside down tree, where we start at the top with what we call the root, and then we move down towards what we call the leaves. It's a very computer science sort of thing to do, to call it a tree and then to like completely screw up the metaphor. But this is roughly why we call it a tree. And so just play along with this computer science game. A lot of times what we'll do is we'll use the language of a family tree in order to describe different portions of the tree. So a family tree, that's sort of an old version here, shows the descendants of a common ancestor typically. So if I can zoom in on that, this is sort of an old school family tree showing everyone descended from one particular matriarch as children are conceived and born, and then marriages create new sub-branches on the way down. So we'll often use the language of the family tree in order to talk about the different portions of the tree. In computer science, the tree is a hierarchical data structure. And so each one of the pieces in the tree is a node. And this is just like a linked list. A linked list also has nodes in it. And a linked list is not hierarchical. A linked list is linear. So a linked list is a linear data structure composed of nodes, but a tree is a hierarchical data structure composed of nodes. In a tree, each node has a sequence of child nodes. And in a computer science tree, the root is one particular node. It is a special node. It is a node that has no parent. Likewise, a leaf is a name for a node in our tree that has no children. So again, imagine that we have an upside down tree. The root is the node that has no parent, and a leaf is a node that has no children. So here's an example of the British royal family tree, always in the news, always relevant. George V at the top, 1, 2, 3, 4, 5, 6 different children along the way. Edward VIII, George VI, Mary, Henry, George, John. If we follow down the left-hand branch, we see that George VI had a daughter, Elizabeth II, who had a son, Charles, who had two sons, William and Harry. And we know that that family tree continues with new children that are the children of William and Harry and their respective spouses. Um, I, this is the British royal family tree. It's helpful in order to be able to understand what it is we're talking about. But I feel like when we talk about family trees a little bit, we are stumbling into some contentious territory. And I just kind of want to acknowledge that no family tree actually looks clean like this. If you actually dig into family trees, you get things that are a lot messier. And so, like, if your family tree doesn't look like this, welcome to the club, right? Even within, I don't know. So here's, for example, Thomas Jefferson's family tree. Thomas Jefferson's family tree is hardly clean. Starts with Thomas Jefferson's great grandfather, Field Jefferson, Peter Jefferson, Thomas Jefferson, his married spouse, his slave with whom he had children, Sally Hemings, and now we have all kinds of descendants. We don't have single marriages. Families have adoptions. We have all kinds of different scenarios in family trees that don't work very well with our computer science definition of a tree, which assumes very clean family trees where no one dies, no one's adopted, nothing like that. Like this, the clean model of the family tree looks nothing like my family tree, for example. I've got an adopted son that taps you into a whole other family tree in really weird ways. We had this situation, which is sort of remarkable, where some people in my family got their DNA sequenced by Ancestry.com. And one of the things that Ancestry.com does is it has kind of a social network built into it when you become a customer of Ancestry.com. And it'll show you, in order to support that family tree, it'll show you people who are customers of Ancestry.com who are also closely matched with you DNA-wise so that you can quickly form connections among your family. Well, so a few people in my family got their DNA sequenced and got some recommendations on who should be in their family tree. And hey, lo and behold, we found out we've got cousins that we didn't know about because of children that were born out of wedlock, I suppose is the best way to say it. And so our family reunion, suddenly we had Debbie showing up, and turns out we've got other cousins as well. And we're like, okay, I guess you're part of the family. It's a little awkward, but here we are. And it's not Debbie's fault, and so she didn't have any significant family, so we invited her to join our sort of annual family reunion. And it's just awkward and weird, and that's how families are, and that's just how life is, and you gotta roll with it and lean into your principles in order to understand how you should react. So anyway, that's just a comment when we talk about our family trees and how they differ from our ideal version. But we use the ideal version when we're talking about the computer science tree. So let's just run down a few of the different vocabulary terms for a tree. And for the record, that those red blocks are the nodes. Down the bottom right, that little answer column on the right with Ann, Peter, Zara, and Savannah, those are nodes in our tree. So we're going to represent our tree like we did our linked list, but with multiple children. So starting with a node. So for vocabulary, a node is a building block of a tree. It corresponds to one red block. It corresponds to one instance of an object whose class is node. And a tree is composed of a number of different nodes which have been linked together, like a linked list, but it's not a list. The nodes are still linked, but not in a list format. So the tree in the previous figure had 26 nodes. Let's see if I can go back. 26 nodes total. So this tree has 26 nodes. There are 26 red blocks. All right, child. Every node has a sequence of links to other nodes which are called its children. So there's a directional property to the links in this tree. And so if we go back and we ask, what are the children of Elizabeth II? It is Charles, Anne, Andrew, and Edward. In this particular tree, this node, Elizabeth II, has 4 child nodes. And they have data that's stored in them, and the data is a string, and the string is a name. All right, a leaf. A leaf is a node with no child nodes. So in the particular representation of the tree that we had on the left, there are 16 child nodes, or 16 leaves, sorry. So here's 1, William, 2, 3, 4 is Zara, 5, 6, 7, 8. All right, now we have to go back up in the tree to find other leaves that don't have children, but which are higher in the tree. So Margaret, 9, Richard, 10, Edward, 11, Michael, 12, Alexandria, 13, John, 14, Mary, 15, Edward the 8th, 16. So did I say 16? Yeah, 16 leaves. So to be a leaf, you don't have to be on the bottom, you just have to have no children. An interior node is the opposite of a leaf. So any node that is not a leaf is an interior node. So basically any node that has 1 or more children is an interior node. A parent node. So if some child is, if there's some node which is a child of some other node, then the node of which it is a child is the parent. So a parent node has some child that hangs off of it. So Elizabeth II here is the parent node of Charles. Charles is the child node of Elizabeth II. And like strictly speaking, it's this node, Elizabeth II is the data in the node. And so it's not that Charles is the child of Elizabeth II, because those are strings. But this particular node object is the child of this node object, and we're just going to reference them by the data that they're storing. All right, sibling, we use the word sibling to talk about 2 nodes that have a common parent. So if we look here, Charles and Anne are siblings because they have a common parent. Andrew and Edward are siblings because they have a common parent. Edward and Michael are siblings because they have a common parent in George. Root. Every tree has 1 root. It is the node that has no parent. And so just by definition, that's the root node. All right, a couple more complex ideas. So a path. A path refers to some sequence of nodes that are connected with a relationship of parent to child. So we talk about them in terms of indices, so C1, C2, C3, all the way up to CK, where every successive node in that path is a child. It doesn't have to start at the root, and it doesn't have to end at a leaf, but they do have to be connected. So here's one particular path through this tree, starting at Elizabeth II, going to Edward, and ending at Louise. So Elizabeth II, Edward to Louise. That is a path that consists of 3 nodes. Each one of the nodes is connected by a parent-child relationship. Here's another path that goes through our data. George V, 1 node. You can have a path with 1 node. Here's another path that goes through our data. George V to Henry. That's a path with 2 nodes. The longest path that's possible in this tree goes from George V to George VI, to Elizabeth II, to Anne, to Peter, to Savannah. That's a path of 1, 2, 3, 4, 5, 6 different nodes. All right, so that's the longest possible path in this particular tree. A descendant abstracts away the relationship between parent and child and says that a descendant is a node. One node is a descendant of another node if there is some path from the ancestor to the descendant. All right, so it's just removing the requirement that two nodes have to be a parent and a child, but there does have to be a path from the ancestor to the descendant. So that covers descendant and ancestor. Another thing that we talk about is a subtree. And a subtree just consists of any set of nodes which are connected and are also connected in the original tree. So on the right here, we see a diagram of a subtree whose root is Anne. And this is a portion of the larger tree that we have extracted to talk about independently. This is helpful for when we start doing recursive algorithms. We start thinking about trees and subtrees. The last thing to talk about is the height of a tree. The height of a tree is the length of the longest path from the root to a leaf. From the root to a leaf. Sometimes you may see other textbooks or other references say that the height of a tree is the number of edges, which would be one less. But for this course, and generally speaking, we're going to talk about the height in terms of the number of nodes. And so this, as I indicated before, the height of this particular tree is 6. All right, that's the British royal family, an abstraction of an actual family and an abstraction even within that actual family so that we can describe how we keep track of a more specific discrete data structure called a tree in computer science. Where are some examples that we encounter this? Well, one real common place where we encounter it is in the file system. So the top figure, figure 2 here, represents a directory tree or a tree of folders. No matter which computer you're working on these days, no matter which operating system, there is a file hierarchy, although sometimes your operating system tries to show you the files in a different way, like through a search interface or through a filtered interface that removes the idea of the hierarchy. But the base and canonical way in which the, hang on, Slack is beeping at me, even though my things are off, and we're just gonna shut it down for the time being. All right. So a directory tree. So what this means is you have folders within folders. So for example, you might have a folder called sample code, and within that you might have two nodes which are also folders called chapter 1 and chapter 2. And then you finally might have folders which are section 1 or section 4, a worked example or a how-to example. Those could be folders, or in a directory tree, typically we think of our leaves being files and our interior nodes being folders. Although I suppose that if you had a folder that had nothing in it, that would be considered a leaf as well in a directory tree. In the bottom is an example of an inheritance tree. We've seen inheritance trees in the Java collection framework, but you might be interested in creating your own inheritance tree. And this is an inheritance tree that maybe describes the way Canvas quiz questions are set up in the implementation of Canvas. So at the top, you might have an abstract kind of class called a question class, and maybe you're going to specialize that in 4 different ways: as a fill-in-the-blank question, a multiple choice question, a question that has a numeric answer, or a question that has a free response essay answer. And all of those would be examples of children of your question class. And maybe you would have an additional child of your multiple choice question, which is a kind of question where you can select more than one answer from the choices that are presented. We'll call that a multi-choice question. So that's a way in which we encounter tree structures in what we've seen other places, in programming languages, in Python and in Java, in inheritance trees. All right, so let's look at a particular implementation of this. And so what we're going to do is we're going to break this down much like the linked list class. And in fact, the linked list can be thought of as a degenerate form of a tree. So if you had a tree where every node only had one child, that would be the equivalent of a linked list. But a tree is going to have multiple children. And so we're going to use a similar structure to the way that we built the architecture of the linked list. And the architecture of the tree is going to have a parent class which holds references to the interior nodes. And the parent class, the overarching class, is going to be called tree. And that's the class we want users of our class to work with. Internally, we're going to implement the node class to help us implement the tree internally. The tree class is going to hold a reference to our root node, just like the linked list class held a reference to the first node in our linked list, and sometimes the last node as well. Internally, our node class is going to hold both reference to the data, so like the string, which is the file name, or the string, which is the name of the British royal family member. And it's going to hold a list of references to child nodes, child nodes, yeah. So here's an example of how we might implement that in the yellow here. Our outer class is the tree class. It's public. We want people to use it. Internally, we have an instance variable, which is of type node, which is a reference that we're going to call root. And that's private because it's only supposed to be used internally within the implementation of the tree class. We'll then define the interior class node as having two instance variables. It has the data that it's storing. We'll give that the type of object, so it can be anything that descends from object. Although we should probably to do this well, we would make this into a generic class instead. And that's what you encounter when you use tree sets or tree maps. Our generic class would replace object with our generic type instead. And our tree definition would have to include the generic type. But just for simplicity, we're going to treat it as objects. Our node class has data as an instance variable, and it has children as an instance variable. Children, you can see we're using the list interface, the generic type, and we're implementing it as a list of nodes. And so in this kind of tree, we can have 0 or kind of infinite number of children. If the size of our children list is 0, then what our node is a leaf. When we allow someone to use our tree class and we implement our constructor, and when someone calls the constructor of our tree class, they pass the data that should be stored in the root node. So notice that when someone calls the constructor as a user of our class, they're not engaging with the node class. What they're passing in is the data that they want stored in the root. Internally in the constructor, the tree kicks off this tree data structure by, number one, creating a new root node, creating a new node, using the constructor for node, assigning root as a reference to the new node, then using the node that's just been created, sets the data to be the data that the user of our tree wants stored in the root. And then finally, it creates an empty data structure to hold any future children. A new array list in this case, could be a linked list as well. For whatever reason, the implementers decided to use an array list. We create that, it has no elements in it, and we assigned children to be a reference to that empty list. So this is helpful. We have a node, we have our root node, it's all set up and ready to add new nodes to it. We've also implemented a particular helper method that is public, that is designed for users of our tree to access, called add subtree. And what this does, again, notice it's abstracting away the idea of the node from anyone that uses it. What it does is it attaches a subtree to the root of this particular tree. So, and it does that by taking in as a parameter the tree that the user would like to attach to this particular node, and it adds to the root this new subtree as a child by accessing the add method of our list interface, adding the root of the subtree. Notice that this particular implementation is going into the subtree, getting the root, and adding the node to the list of children. So it's sort of getting rid of that outer shell of the tree as it adds data to this tree. All right. This sets us up well for doing recursive algorithms. So when we do computing on a tree, it's very common to use recursion in order to do the work that we want to do. Recursion needs a couple properties. It needs to make sure that each time we call a recursive call, that our problem is getting smaller. And so the way this typically works in a tree implementation is that each time we call our recursive call, we're calling it on a subtree of our existing tree. So the tree is getting smaller and smaller and smaller as we walk down the data structure. Eventually, our ending condition, the other thing we need for a successful recursive algorithm, is that there are no children. If there are no children, we can't do any more recursive calls, and so we're done with the recursive call. Then we return, having calculated whatever we want, and as we return from the successive recursive calls, we capture whatever data we were interested in. We do whatever work we wanted to know about our subtrees and compile that, aggregate that, and then return that as our result. So anytime a particular method works on a tree data structure, it doesn't know whether it's being called recursively or whether it's being called on the actual root of a tree. It shouldn't matter. The answer should be the same. All right, so for example, if we would like to know the size of a tree whose root is R, but whose children are C1 through CK, we can do this by recursively making a particular kind of call. We know that the size of a tree is 1, at least. That is the node whose size is currently being asked for. So in the implementation of a tree, we will ask, how big are you, tree? And the tree will say, well, I'm at least 1 because I've got the node that's currently represented here. But to that 1, I also need to add the size of all of my children. So in addition to me, I'm going to add the size of child 1, the size of child 2, the size of child 3, all the way up to the size of child CK. And by adding up the result of these recursive calls on all of my children, I will get my entire size, myself and all of my children included. And I will return that, returning that perhaps to the initial call of my size request, or perhaps I'm a recursive call myself, and I'm going to be summed up with all of my siblings as well. Doesn't matter. That's the beauty of recursion. So let's look at how we might implement our size call recursively. What we'll do is we'll create two different size methods. And so from an architectural standpoint, you have to watch this move carefully. There is a size method that is in our node class, and there is a size method that's in our tree class. The size method that's in our tree class is the one that we expect users of our class to use. The size method that's within our node class is one that's just helpful for us and that we've implemented on our own terms. Micro coffee break. All right, so let's start by looking at the bottom chunk of code. This is what someone who wants to know the size of a tree is going to call. They'll have some tree reference, maybe it's t, and they're going to say t.size. That's the method they'll call, and then it will kick off the recursive calls to calculate the full size of the tree. So the first thing that happens is in this tree outer class, we check to see whether there's any data that's being stored in this particular node. If root is null and there's no data that's being stored here, well, then this node isn't a valid node, and we just return 0. Notably, this is sort of a degenerate condition. This is a tree with no data in it. Otherwise, we're going to return the size of our root. All right, so now careful here. That else condition in the bottom yellow bracket, that's not the recursive call. If we call root.size as part of the return statement, return root.size, notice that root is a reference to a node class. So the size method that's being called in the return statement in the tree class is a call to the size method in the node class. So this point right here is where we jump and kick off an internal recursive call on our node. Okay, so now we're in our node and we're going to say, what is the size of our node? And this is where the sort of real recursion happens. We're going to start and we're going to create an aggregator variable, which is 0. So that's our base. And then we're going to create a fast enumeration that walks through each of our children. Children is the name of the reference to our list of nodes. And so each time we go through this list of children, we will have a reference child, and that will be reset each pass through the loop. What we're going to do in each pass through this loop is we're going to update our value of sum to be whatever our value of sum was before in the last iteration of the loop, plus the size of the current child. Now this call is a recursive call because child is of type node, child.size is going to call the size method on the node class. Here's our node class, here's the size method, and so now we are recursing down the tree. And so now we're asking, what is the size of our subtree? And the size of our subtree, and the size of that subtree and subtree, all the way down until we get to a point where we get to some node that has no children. What's the name for a node that has no children? In the vocabulary that we've been using, a node that has no children is a leaf. Is this line going to work okay if we have no elements in our children list? Yes, it will work okay. It will work okay because when we initialized it here to be an empty array list. So it's not null, it's just empty. And it will work okay because when we do this fast enumeration, children is empty, and so this loop will never actually get the body of this loop will never get run because there's no children to run it on. But there is a list, and so it's just a list with 0 elements. So we won't get a crash and we won't get this body of this loop run. Sum will be equal to 0, and we will return 1 plus 0. So when we get to our leaf node, we're going to return a 1, and this is our ending condition. So this is how our ending condition works out. Our ending condition is the situation where we have no children and we return 1 and make no recursive calls. Our smaller situation is when we do have children and we make the recursive call on a smaller problem here. All right, so as we return from calling child size on all of our children, sum adds up the results of all of those recursive calls, and eventually we're done with our children. We add 1 to that sum for ourselves, and then we return from maybe a recursive call, or maybe it was the original call. And if it was the original call down here, then the size of the tree is now answered for us. Really, really beautiful and elegant kind of algorithm here. I heard typing in game, so let me check to see if there's active questions. Okay, I don't see anything. Okay. So let's just walk through some of our vocabulary, do these kind of quickly. What are the paths starting with an in this tree shown in figure 1? The paths starting with an. All right, well, an is not the root node, an is right here. And so as we look at the possible paths, we have a path of length 1, that's Anne, a path of 2, Anne and Peter, Anne and Zara, and a path of 3, Anne, Peter, and Savannah. So the key thing in here is that we say paths starting with Anne. If we had asked for all the paths in this tree, there'd be many, many, many different paths. A path can have one node, a path can have multiple nodes, a path does not have to start at the root, a path does not have to end at a leaf. But the path does have to have a sequence of nodes that have the parent-child relationship. Notice that we're working about these things in two different ways. In one way, we're thinking about this structure of a tree abstractly, and in this way that's separated or disconnected from the implementation. And then the other way that we're thinking about it is how do we do these algorithms in a particular implementation? And being able to understand what we're doing abstractly is important because our implementation will vary based on the languages that we're using. Here's a question. What are the roots of the subtrees consisting of 3 nodes in the tree shown in figure 1? What are the roots of the subtrees consisting of 3 nodes in the tree shown in figure 1? So the first thing you have to know is what a subtree is. You have to know what a node is. You have to understand how a subtree can contain 3 nodes. Well, here's one. Edward, Louise, Severn. That's a subtree that has 3 nodes in it. Well, can we find other subtrees that have 3 nodes in it? Yeah, well, here's one, Andrew, Beatrice, Eugene. That's good. And here's one, Charles, William, and Harry. The subtree needs to take all of the children with it in order to be an actual subtree of this existing tree. So for example, we can't say that Anne, Peter, and Savannah is a subtree consisting of 3 nodes, because a subtree has got to take all of the components of the tree with it. So the subtree rooted in Anne would have 4 nodes. And I don't see any other subtree that contains 3 nodes. The subtree has to take everything from the root down to the leaves when we grab a subtree. Unlike a path, right? A path doesn't have to take everything, but a subtree does. What is the height of the subtree with root an? Speaking of an, so the height of a tree or a subtree is the length of its longest path. So rooted in an, here's 1, 2, 3. That's the longest path from a root to a leaf. Height is 3. Anne, Peter, and Savannah. What are all the possible shapes of trees with height 3 and 2 leaves? Okay, so these are all trees of height 3. It's not all possible trees of height 3, but it is all possible trees of height 3 that have 2 leaves on them. Here are the leaves on the first tree. Here are the leaves on the second tree. This all has a height of 3, even though not all paths are height 3. And here's the flip, a mirror image of that here. So here's one with 3 as well. Okay, great. So here's an example of how we could use our code in order to build a tree. So using our public interface that we just described of our tree class, how would we construct a tree that's identical to the subtree that's rooted in an? All right, well, we know we have to call some constructors. We know we have to do some subtrees. So here's how we do it. We start by using the public interface to construct a tree that has an as its root data. That's T1. Keep a reference to it around in T1. Now we're going to create a new separate tree that has the root node of Peter. After we make the second call, there's no relationship between T1 and T2. But now what we want to do is we want to connect them. And so we're going to say T1 to T1, we're going to add the subtree at T2. So this is going to look into T2. It's going to grab the tree rooted at node, and it's going to attach it as one of the children to Anne. So now Anne and Peter are connected, and we get just sort of a 2-node connection here. Let's now create a third tree rooted in Zara, disconnected from all our other references. And now let's graft it in. So to T1, we're going to add T3. So now T1 has had 2 trees added to it. T2 rooted in Peter and T3 rooted in Zara. So that gets us our first 3 nodes here. Now we're going to create a 4th tree rooted in Savannah, call it T4, and we're going to add it as a subtree not to T1, but to T2, which had the data Peter. And so when we're done writing this particular code, running this code, we're going to have a data structure that reflects this chunk down here of the tree. All right. Talked about that. All right, so now what I want to do is I want to restrict the kind of trees that we're talking about. Up until now, when we were talking about a tree, the assumption was that the tree could have as many children as we wanted it to have. And we kept track of them internally within the node class using an instance variable, which was a list of children. In introducing the idea of a binary tree, what I want to do is restrict our trees so that each node can only have 2 children. And we're going to call them the left child and the right child. Turns out that this restriction does not restrict us in terms of representational power from what we had before, but in many ways it's cleaner and easier to reason with than a tree that has an arbitrary number of children. Checking in. Sam asks, could you attach Savannah to Peter, then attach Peter to Anne? Let me see. Could you attach Savannah to Peter and then Peter to Anne? Savannah to Peter and then Peter to Anne. Yeah, absolutely. Yeah, you could do that because internally the nodes are what's happening. So you don't have to build this thing from top to bottom. You just have to make sure that you're adding the connections. So what your add subtree is doing is making a connection between nodes. And so it's sort of like, it's a little bit like you're adding nodes to a linked list, but you're doing it in a slightly different manual way that reflects the fact that it's not a linear structure. As in create Peter, attach Savannah, then attach them both to Anne. Yeah, you could do that. You don't have to, once you've attached Savannah to Peter, you don't have to attach Savannah to Anne because if Savannah is attached to Peter and you attach Peter to Anne, then the connection between Anne and Savannah is already present. All right. So here's one particular way in which we can use a decision tree that's kind of fun. We can use a decision tree to answer questions using them to decide among a number of different options. For example, this problematic picture of a person choosing which shoes to wear. In our decision tree, what we can do is we can represent our decisions as each node in our tree, each non-leaf node contains a question. And because this is a binary tree, we can say that our left subtree is going to be a yes answer to the question. And a right subtree represents a no answer to the question. And every node is either going to have 2 children or no children. Either it's a question or it's an answer to the questions above it. So here's how we might do a decision tree for an animal guessing game. At each node, we might ask a question, and then we would recurse down the appropriate path in order to ask a more detailed question. So we might ask, is something a mammal? No. Does it fly? Yes. Then we presume it is an eagle. Is it a mammal? Yes. Does it have stripes? No. Then we guess that it's a pig. And if at any point, like if we were going to make this in sort of a style of a machine learning algorithm or something, or if you've ever played the 20 questions game that's on the web, if you ever get to a leaf in this decision structure and you're wrong, for example, you ask, is it a mammal and does it fly? And you say yes, therefore it must be an eagle. And the person who's playing the game says, no, it's not an eagle, it's a dove. Okay, so then you would have to ask some sort of new question that would differentiate an eagle and a dove. So you might say, is it used as a symbol of peace? And if it's yes, then you would ask a new question. You would put a subtree under does it fly, and the children of is it a symbol of peace would be yes, dove, no, eagle. And maybe you'd find other ones. And so this tree would grow as you get more specific and your answers get better and better and better. All right, so another example, I'm going to stop here, but just to leave us where we're going to pick up next time, another example of a way we can use a binary tree is something called a Huffman tree. And a Huffman tree is used for compressing files. So if you've ever used like the zip format of a file compression algorithm, one of the ways that compression can happen in a compression algorithm like zip is by using a Huffman tree. And we're going to describe that next lecture. So to wrap up for today, let me just reiterate kind of where we were, or where I am, where you are, where we all are. We're talking about trees. Trees is a particular kind of data structure in computer science that is roughly mimicked on a family tree. There's a particular language and vocabulary that we use to talk about trees. We think about them both abstractly as we think about algorithms that we want to do work on the tree, and then we implement them in particular ways. We've seen one particular implementation. A tree is very much like a linked list, except that it has more than one way to go when you go right. And a binary tree is a specific kind of specific kind of a tree data structure that only has 2 children. Okay, so there's going to be a assessment that I'll throw up after class. I had to see how far we got today. That's going to ask you a bunch of questions about the vocabulary that we went over today, and then help you review that. And you can do that anytime before midnight tonight. All right, so let me just formally say thank you for your attention today. This is the end of class. I will stick around and answer any questions that you have, but if you need to take off, feel free to do so. Thank you for your attention today. Okay, double broadcasting for a second. for a second. All right, double broadcasting in game. This is the end of class on 421. We were talking about trees, introducing the idea of trees and binary trees. The last question that we had that was just on in game, wasn't on YouTube, was how does the recursive call in this particular size method end? And that the answer to that is we typically see recursive calls ending with some kind of if statement that when it's true, we just return right away. This particular code doesn't need an if statement because built into this loop is an implicit if statement, which is the following. If children.size equals 0, then there will be no fast enumeration through that data structure, and so this code will never get run. And since this is the only recursive call, if children.size equals 0, this doesn't get run. There's no need to have a separate ending of the recursion if statement. We just are going to end up skipping this when we get to a leaf and immediately returning. So it's not, when we talk about recursion needing two requirements, the problem getting smaller and an ending condition, it's not necessarily the case that the ending condition has to be really explicitly put out here in an if statement. It can be just part of the way the code flows along the way. Okay, so with that, we're going to wrap up our YouTube broadcast. And I am going to come over here to take attendance in game. Dodgers running around. It is a good day. All right, thank you for your attention. Shutting down broadcast.